So we're considering candidate inner products here. We want to see whether or not, again, candidate inner product actually has what it takes to be an inner product. All right? We're working here in the real number spaces. So I'm not going to write the complex conjugates because I don't need to here. All right? We could modify any of these candidate inner products just by putting complex conjugates on the first contributions and make them work with complex numbers. All right, but I'm just not going to do that here because we're only working with real numbers for the time being. All right, we're working in R3. So that means each of our vectors has 3 components. I am going to indicate those components with a script. Okay? So I've got u1, v1 plus 5, u2, v2 plus 3, u3, v3. And I need to verify the 3 properties of inner products. Okay? Property number 1. The inner product is linear. Linear. All right, so we would be led to consider the inner product of u with, here I can't use subscripts, so I'm going to use a different letter. CB plus KW. All right? So what do I get? Well, this is going to be U1, CB1 plus KW1 plus 5. U2, CV1 plus, 2 plus KW2 plus 3 U3 CV3 plus KW3. Now, each of these contributions to the inner product takes the form of a number times this sum. If you remember from our discussion of linearity weeks ago, multiplication by a constant is the only fundamentally linear operation. So when we're trying to build linear operations, we piggyback on that operation. We did the same thing when we defined the determinant. All right? We used the fact that multiplication by a constant was the only linear operation. So here I'm going to exploit the linearity in multiplication by u. We call this the distributive property. So I'll say C u1 v1 plus k u1 w1. 5 C u2 v2 plus 5 k u2 w2 plus 3 C u3 v3 plus 3 k u3 w3. And now I'm going to use the commutative property of addition to rearrange these terms. And then I'm going to use the distributive property to factor out a C and a K. So I would get C u1 v1 plus 5 u2 v2 plus 3 u3 v3 plus k u1 w1 plus 5 u2 w2 plus 3 u3 w3. And by our candidate inner product, this is going to be C U inner product with V plus K U inner product with W. And that's what we wanted. So that indicates that this candidate inner product is indeed linear. Validating property 1. All right? So I'm going to erase all this business. All this was us just verifying explicitly that multiplication by a constant is linear. That's really all this was. All right? This all follows from the fact that we were multiplying by U1, 5U2, 3U3. Okay? Each of those operations is linear. So I'll get C, U with V, K, U with W. All right? So checks out. What about symmetry? Remember, you don't need to worry about the complex conjugate for the time being. So symmetry, we're looking to consider V with U. I mean, that's just going to be V1, U1, 5, V2, U2, 3, V3, U3, which by the commutative property of multiplication is just U with V. So that's clearly symmetric. All right? What about positivity? Well, U inner product with itself would be U1 squared plus 5 U2 squared plus 3 U3 squared. All right? Now, once again, we're only working with real numbers. The square of any real number is non-negative. Greater than or equal to 0, greater than or equal to 0, greater than or equal to 0. If I add them all up, guess what? I'm going to get something that's greater than or equal to 0. Moreover, the only way that it could equal 0 is if each one of the contributions was 0. So that means that the only way that the inner product of a vector with itself could be 0 is if all of its components were 0. And that implies that U is just the 0 vector. And that's what we wanted. So this candidate inner product satisfies all 3 properties defining an inner product. And it therefore does represent an inner product. Okay? Clearly, we could have changed this 5 and that 3 to be certain other numbers. All right, so this would indicate that the candidate inner product that one also would work in R3. Okay? Now, we can understand at least from one perspective, why it is that we might be interested in using this inner product instead of the standard inner product, just by looking at the results of an experimental of the results of an experiment, okay? Certain measurements. Suppose that I wanted to fit data to a line. All right, and let's say that my 3 data points were these. All right, or this is an error bar. The second measurement was difficult to measure. There was something going on, all right, in the machinery that made it difficult for me to pin that measurement down. So if I was trying to do a best fit line, like a least squares problem with this data, clearly I want this information to be more important than this information. All right, and I want this information to sort of have an intermediate importance. That's what this inner product does. All right, it says that the first component is more important in the inner product than the other two. Okay, we can do a weighted error analysis by using an inner product of this form. So that gives an indication of why I might care about a non-standard inner product. Okay? Now, I can't just change these things however I want to, because what if I had this candidate inner product? Here, we run into a bit of a snag. Not with linearity. This inner product is perfectly linear. It's also symmetric. So why am I saying there's a problem? Well, because of property 3, positivity. Property 3 is often the one that's going to lead to trouble. Property 3 is the most simple of the 3 properties. Okay? We want to pay close attention to that one, because there are lots of candidate inner products that satisfy properties 1 and 2, no problem. But they violate property 3, and we need to look out for that. All right? In this situation, we could consider the inner product of this vector with itself. And what would I get? Well, I would get 3 times 0 times 0 minus 1 times 1 plus 8 times 0 times 0. All right, essentially what I'm doing when I choose this vector to look at is I'm muting these 2 contributions. These 2 contributions are yelling 3, 8. All right? So if I don't shut them down, then they might wash out the contribution from this middle guy. And this is the offensive contribution. All right? So when I'm deciding on a counterexample, I want to focus on the thing that might be the problem. All right? This, of course, is an issue because you can't have an inner product of something with itself be negative. All right? That doesn't work. All right? Let's look at another example. Let's just do this in R2. So what do you think? Will this one be an inner product or not? Well, I mean, it's clearly linear. Notice I've got 5u1, and then I would multiply by a sum. u1, I would multiply by a sum. 8u2, I would multiply by a sum, right? I would distribute, I would move the terms around, and it would be perfectly linear. So linearity isn't going to be a problem here. Notice that positivity also won't be a problem here. Why not? Well, because u with u would be 5 u1 squared plus u1 u2 plus 8 u2 squared, right? All right? So if I wanted to show that this works perfectly fine as far as positivity is concerned, then I could say this is equal to 1/2 u1 plus u2 squared, right? Plus 9/2 u1 squared plus 15/2 u2 squared. Sort of like completing the square to pull this cross term, which is the only one that's not positive definite, into a square. And now I have it as a sum of 3 positive definite contributions. This is clearly positive definite. So no problem with linearity, property 1. No problem with positivity, property 3. Now, if you're paying attention, you should notice that I have explicitly skipped over one of the properties. All right? And that was property 2. Symmetry. I mean, come on. This is an explicit violation of symmetry. U1, V2. That ain't gonna work. All right? So this violates symmetry. All right, let's try another one. All right. So let's go through this one.